Hello, and welcome to our final project demonstration for DATUM, an embedded system for range finding and thermal imaging. Our goal is to build a low-cost, portable mapping platform that utilizes ultrasonic and thermal sensors with a touchscreen interface. We'll show you how DATUM measures range, maps collected data to a live visualization, and how it calibrates itself using environmental data. Throughout this video, we will explain our design decisions, demonstrate our prototype, and discuss results.
Here's the roadmap for our presentation. First, we'll give a brief project overview and list the requirements we set out to meet. We'll then describe the hardware architecture, followed by the software design and implementation. Next, we'll walk through the test methodology used to validate our system and present the results. Finally, we'll reflect on our achievements and limitations and discuss future work.
DATUM uses an ultrasonic distance sensor, a 2.8-inch touchscreen, a stepper motor, and an environmental sensor to build a 3D map of its surroundings. The LCD shows a visualization of DATUM's surroundings in real time. The system is designed to be modular and low power, so it can be easily modified and implemented anywhere. When we wrote our proposal, we identified 8 key requirements. We needed range accuracy from 2 centimeters to 4 meters within plus or minus 1 centimeter. We planned 2-axis scanning for full 3D coverage, though our prototype only implements horizontal motion. Our firmware converts range data into coordinates and plots them on the LCD. Thermal mapping using an infrared array is included in the design, but not yet integrated. We use temperature and humidity sensors to compute the speed of sound and calibrate our measurements. The user interface is fully touch-driven. The system is powered from a 12-volt supply with 5-volt and 3.3-volt rails for all the components. And we designed a 3D printed payload to mount all components. Most of these requirements were met. Thermal mapping and vertical scanning, however, remain future work.
Hardware architecture. Here's a diagram of the hardware architecture. At the heart is an STM32L476 microcontroller that provides enough processing power while consuming little energy. The ultrasonic module measures distance by emitting a pulse and timing the echo. An MLX90640 infrared array is wired in but will be used in future versions for thermal imaging. The stepper motor rotates the sensor platform in azimuth. We use a 2.8-inch color LCD with a resistive touch overlay for the user interface. Environmental temperature and humidity sensors feed into the microcontroller via I2C to calculate the speed of sound for calibration. All components are powered from an onboard power regulator, which generates 5 volts and 3.3 volt rails. The payload is entirely 3D printed, providing a lightweight and modular structure.
Our firmware follows a cooperative scheduling model. Upon startup, the microcontroller initializes all peripherals and displays a menu on the LCD. Before the scan, DATUM reads temperature and humidity from the environmental sensor and computes the speed of sound. This value is used to convert echo time into a distance. The stepper motor rotates the payload to the next position. We then trigger an ultrasonic pulse and capture the echo using a timer. The measured distance and angle are converted into X and Y coordinates. A planned feature is to read the infrared array for temperature at each point. The point will then be colored on the LCD according to its temperature in real time. The loop repeats until a full scan is completed or the user stops it. A cooperative scheduler ensures that each task yields control so that the user interface remains responsive.
Implementation and modules. The code is modular to simplify maintenance and extension. A cooperative scheduler coordinates tasks such as motor stepping, sensor reading, and UI updates. The GUI module renders menus, buttons, and the polar Cartesian plots on the LCD and handles touch input. The stepper driver generates precise control pulses. The stepper resolution is 0.0879 degrees per step. The ultrasonic triggers pulses and measures the echo using input capture and DMA. Environmental sensors read temperature and humidity via I2C and compute the speed of sound. This modular approach allowed us to develop test subsystems independently and will make it easier to integrate additional sensors in the future.
We devised a series of tests to verify DATUM's performance. For range accuracy, we measured distances from 2 centimeters to 4 meters against a tape measure and computed the error. We calibrated the speed of sound by comparing the raw ultrasonic timing to the expected speed based on ambient temperature. We measured the stepper resolution and verified that each step corresponds to 0.0879 degrees. In the final dual-axis system, we will generate point clouds and save them for inspection to verify map generation. Finally, we measured current draw during scans to ensure the system stayed within our supply limits. Each test had an expected outcome, such as an error below plus or minus 1 centimeter and a current draw below 700 milliamps.
Results and analysis. Our results show that the ultrasonic rangefinder meets the accuracy requirement. Measured error remained between 6 and 9 millimeters across distances from 0.5 to 4 meters, well within the plus or minus 10 millimeter threshold we set. Using the environmental sensors to compute the speed of sound reduced systematic error to a few meters per second. The stepper motor resolution measured at 0.0879 degrees per step, matching the data sheet. Current draw peaked at about 450 milliamps, safely below our 700 milliamp limit. Overall, these results confirm that DATUM performs reliably and efficiently.
Our prototype achieves real-time ultrasonic scanning and mapping on a low-power microcontroller. The environmental calibration improves accuracy with minimal cost. The touchscreen interface makes operation intuitive, and the entire payload is modular and 3D printed, so improvements will be easy to implement. Some planned features, however, remain unfinished. At present, the payload only rotates horizontally. We have not yet added the vertical servo to perform 2-axis scans. The infrared array is wired in but not integrated into the scanning loop, so thermal mapping is still pending. Additionally, integrating a LiDAR sensor will allow for more accurate range finding in some environments. A final limitation is that of a limited memory on the microcontroller, which caps the number of points that can be stored in the point cloud.
Conclusion and future work. In conclusion, DATUM demonstrates that an inexpensive, embedded platform can achieve accurate 3D mapping by combining simple sensors with clever calibration and software design. The cooperative schedule, modular firmware, and touch interface create a foundation that can be extended for several applications. Looking forward, we plan to add a vertical servo to enable full 2-axis scanning, integrate the infrared array for thermal imaging and data fusion, optimize memory usage to store larger point clouds, and incorporate a LiDAR module for extended range and robustness. Thank you for watching our demonstration.